Welcome to Algebra 2. This is section 5.3. We're graphing radical functions today. All right, so a radical function is just a type of function that contains a radical expression in it. So it might be a square root, a cubed root, or something like that, but we call those types of functions their specific root function, like a cubed root function, a fourth root function, or a square root function. And we've seen square root functions early on. We first started talking about chapter 1, parent functions and transformations. So we will see a little bit of transformation work here today as well. Just a couple of helpful pointers. We're going to graph these by making a table of values for the most part, and we can save ourselves a lot of time by thinking what are nice values to put under a square root or under a cubed root, etc. So I've given you a couple of nice square root approximations that'll help you plot points if needed. The square root of 2 is about 1.4, and the square root of 3 is about 1.7. Those will help you approximate points when you're plotting them. But again, think about what would make perfect squares or cubes underneath a square root or a cubed root. That way we'll get nice, clean outputs. So it may be helpful to make just a short list of what are perfect squares. Okay, we could put 0 under a square root, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So all of those could go under a square root and produce a clean output. We could also have perfect cubes that go in. They're not as common as perfect squares, to recognize them easily. But we could put 0 under a square root. We could even put negative numbers under a cubed root. Remember, it's an odd root. That's okay. So we could have 0. We could have 1 cubed. We could have 2 cubed. We could have 3 cubed. We could have 4 cubed, 5 cubed. And that could go in a positive or negative direction because a cubed root accepts negative inputs. All right, so having those numbers at our disposal will help. And then number 2, we're going back to parabolic charades. Guys, that stretching and shifting and reflecting stuff, that's true for these functions as well. So that is very helpful to help us describe a graph, know what it should be doing as we're graphing them. So a bit of textbook information for you. What does a parent square root and a parent cubed root function look like? What do they have for domain and range? Well, we know that with a square root, in order to plot that on a real coordinate plane, we can't have negatives going into our square root. So our domain has to be x's that are greater than 0. And then the outputs, if I'm only taking the positive square root of numbers, the range is also y values that are greater than 0 only, or equal to 0. We can plug 0 into a square root just fine. For a cubed root, however, we can plug in any number we want to, positive or negative, and we will get a real output. So our cubed root function has a domain and range of all real numbers. You can see that graph extends all the way across the page. It would continue to rise to the right and fall to the left. So again, that'll help us know what our graphs should be looking like. All right, our rules from charades, our typical stretching and shifting and reflecting patterns, those do apply, so I've included those for your reference. They still have not changed one bit. Are we adding something to the input? Are we adding something to the output? Are we multiplying something to the input, multiplying something to the output? And are we negating the input, negating the output? All of those still apply. So hopefully you have a nice foundation with that knowledge. All right, so for number 10, it says graph the function and state the domain and range. Well, let's just kind of imagine what we're seeing. We're seeing a parent square root function in number 10, and then we're subtracting 5, but that is not grouped in with x underneath the radical. It is outside. So I'm thinking, oh, it's just going to look exactly like the regular square root function, except it's shifted down 5 units. All right, so that's going to help me understand what my graph should end up looking like. And let's go through and make just a quick little table of values here. Well, whatever my input is, I'm going to be taking the square root of it. I know I can take the square root of 0. I know I can take the square root of 1. take the square root of 4, and I can take the square root of 9. So let's pick those as inputs and see what the outputs would be. If I take the square root of 0, I get 0, and then I subtract 5, negative 5 is my output. All right, next, if I take the square root of 1, that's 1, subtract away 5, that's negative 4. If I take the square root of 4, that's 2, subtract away 5, that's minus 3. And if I take the square root of 9, that's 3, subtract away 5, that's minus 2, negative 2. So by choosing those inputs carefully, I get nice clean outputs. Let's see what that graph looks like. 0, negative 5, right about there. And we're at 1, negative 4, 4, negative 3, and then 9. This is only an 8 square grid, so 9, negative 2 would be somewhere over here. But if we connect those points, you can see that our graph looks just like the parent function for square root, except shifted down 5 units. So the transformation agrees with the table that we made. What's the domain? What's the range? Well, let's look at our graph. Our domain is all x values that are greater than or equal to 0. And we can tell just by looking at the x-axis. What numbers on the x-axis will lead us to the graph? We don't see any graph over here to the left, but as soon as we get to that y-axis, when x equals 0, we start seeing our graph. What about for the range? Yeah, we'll use a different color here. For the range, now I'm looking at the y-axis. Where am I going to see the graph? I do not see the graph compared to the y-axis way down at the bottom, but as soon as I get to this height and up above, then every y value will be hit, and that graph will continue to rise to the right. So my range is all y values that are greater than or equal to, right now it looks like negative 5. And if you think back to our parent function, that should make perfect sense, because with a square root function, our domain and range did have a definitive starting point, and then they either rose or fell from there. For number 16, here we've got negative 3 times x plus 1 to the 1/3 power. I'm just going to rewrite that. This g of x is like negative 3 times the cubed root of x plus 1. It just more clearly shows me what root is acting on this function. So I know I've got a cubed root function. Let's make an xy table. Well, here there's a little bit more thought involved. I want to create a perfect square or perfect cube underneath that cubed root. That means I need to pick a number that is 1 less, because underneath I know that whatever I choose as an input, as an x value, I'm going to have to add 1 to it, and I hope that makes a perfect cube. So let's try negative 9, and then how about negative 2, negative 1, 0, how about positive 7? If I choose those 6 inputs, I think I'll get nice clean outputs. Sorry, those 5 inputs, I think I'll get clean outputs. Now for the y value, if I plug in a negative 9, I'm going to have the cubed root of negative 9 plus 1. That's the cubed root of negative 8. That's negative 2. And don't forget about that times negative 3 out front. It'll be a positive 6. If I plug in a negative 2, then I'll be taking the cubed root of negative 1, which is negative 1, times negative 3. That's a positive 3. If I plug in a negative 1, I get a cubed root of 0. That's just 0. And times negative 3, it remains a 0. If I plug in 0, I get cubed root of positive 1, which is 1, then times negative 3. Plug in a 7, I'm going to be taking the cubed root of 7 plus 1, that's 8, cubed root of which is 2, times negative 3, negative 6. So smart inputs make the calculation very easy to do in your head, and we have some, charades lingo that'll help us. I'm thinking vertical flip. That graph is 3 times as tall, and it's also shifted 1 unit to the left. So hopefully we see a typical cubed root function with those attributes. And again, we've got the parent functions to compare to. So here I am at negative 9. we're up at positive 6. There's 1 point. At negative 2, I'm up at a height of 3. Negative 1, 0. 0, negative 3. And 7, negative 6. So my graph kind of looks like this, bending through like so. The domain of this function is all real numbers. And the range, also all real numbers. We can tell that that graph goes in both positive and negative directions, xy's, and it also rises to the left and falls to the right, so it will cover all the heights on the y-axis. Cool. So that's our first task, and probably our most, laborious task is to graph these functions by hand. Next, just describe the transformations. Here we're just looking for what's happening outside of our parent function. So here I'm starting with a square root x. I'm multiplying a 2 out front and subtracting a 1 in with x. Well, that minus 1 in with x is telling us it's going right 1 unit. And that 2 out front says it's twice as tall. 2 times as tall. All right, for the second one, we're starting off with a 5th root of x. That's our parent function. And what's happening to it? Well, the input is being negated. That's a horizontal flip. The input is being multiplied by 32. That means it's going 32 times as fast. Right? Input is speed or time, 32 times as fast, or it is 1/32 as wide. If it's taking less time, that graph is going to be really shrunk left to right. And then outside the root, we have a +3. That just means up 3 units. So this is the same stuff we talked about in Chapter 1 and Chapter 2. It's back at us again here in Chapter 5. And we even covered it in the end of Chapter 4. Example 3 says use a graphing calculator to graph the function, then identify the domain and the range. So now instead of having to use a table of values to graph, now we're going to use a calculator. So let me pull up my calculator here. Let's go through how to type this in. So in our calculator, we could hit the math key, and you can see there's a cubed root. It's option 4. So you can do that if you want to. I'm going to actually choose not to do that because I'm going to show you a method that works for any calculator. So let's quit out of that. I'm going to go to y equals, and I'm going to type in parentheses, I want 1/2, that's 0.5, x squared minus 3x plus 4, and I want all of that being cubed rooted. Well, we just got done talking about how taking the cubed root is like raising something to the 1/3 power. That's our way of typing it in any calculator. And I'm sorry, this screen is kind of small, but putting that 1/3 power in parentheses, that gives me the same thing as a cubed root. So let's graph it. We should see a pretty typical cubed root function happening here, but they're doing some weird things inside. Oh, so there it's bending like a cubed root. But again, the stuff inside is kind of distorting that graph a little bit. Okay, so let's describe the domain and the range of this graph. What I need to do to get a better look at what's happening, I can tell what's happening left to right. I can count those tick marks pretty easily. But I'm going to adjust the window. And for my y-axis, I don't want it to go from -10 to 10. Let's have it go from -3 to +5. And if I graph that, now I should be able to see the graph will be kind of stretched a little bit, but we'll be able to see a little bit closer look at what's happening here. Okay, so let's describe what's happening on this graph. Hopefully it'll let me write on top of the calculator, I'm not sure. But if I'm trying to find the domain and the range, the domain, it extends all the way across the screen, just like a regular cubed root function. Anything is allowed in, so all real numbers works. But now, since I'm not just plugging in some x value, it's an x squared, there's like a quadratic inside that cubed root, you can see that that's doing something different for the outputs. My range, if I look at the y-axis, it looks like the lowest, oh, it will let me write on that. The lowest I reach on the y-axis is a -1, and then the graph's going to keep rising up above that height of -1. So my range is all y values that are greater than or equal to -1. And if we really wanted to confirm that, we could use calc-min on the calculator. We got a couple of videos showing how to do that as well. So calculator helps us make short work of the graphing. That would be a really tough table of values to interpret. All right. Example 4. Here we need to write a rule, and we've seen problems like this earlier on, except they were mainly quadratics or other types of functions. Now our functions are just going to have radicals in them. Let G be a reflection in the y-axis. Okay, let's see what they mean by that. That's a horizontal flip. Right, reflecting across the y-axis means I'm going from left to right. So after we do that, we're going to do a translation 1 unit to the right. Okay, so those are the two things we need to accomplish. We're starting off with f of x. Okay, so it's a followed by problem, and we've talked about those earlier. That means that I'm going to handle one first and then the other. The order matters. First thing I want to do is a reflection in the y-axis. So let's use h of x as a stepping stone here. That's going to equal the reflection in the y-axis of f, what I'm starting with. And I do that by taking function f and flipping the input. So h of x is really going to be 2 times the cubed root of -x minus 1. Now let's do the followed by part, the 1 unit right. Okay, well now g of x is going to be my result from last time, h of x, but I need to adjust the input to go 1 unit right. That means x minus 1 for an input. And that means that my g of x is going to equal 2 times the cubed root of not -x plus 1, but -x minus 1 minus 1. I don't know why I said plus 1. It was always a minus. But that should be my final function. And yes, there is some cleanup work. We could distribute and combine like terms down here to clean that up. But really, for our purposes in this class, I like this as a final answer. I think this clearly shows that you see the horizontal flip followed by adjusting that input further by taking it not just x, but x minus 1. All right. So in number 50, we're still doing the same thing. We're starting off with f. Here's the function we're starting with. And then they tell us all the different things we need to do. We need to negate our input, multiply the whole thing by 1/4, and then add 6. So I've got 1/4 times that cubed root. Sorry, this is what g of x is going to be. 1/4 times that cubed root. It's not going to be x that's squared. It's going to be -x that's squared. It's not going to be plus 10 times x. It's going to be plus 10 times -x. And then I'm going to add 6 outside. All right, so here they pointed out everything that we needed to change. We just need to make sure that we are doing that in the correct order, not breaking the order of operations. But that g of x in green is our final answer. And we're going to learn these transformations inside and out, use that knowledge that we already have. All right, the final example, example 5, here we have functions that aren't solved for y already. So we have to do a little bit of work before we graph them on the calculator, and then we're just going to describe what the graph looks like. All right, so let's start with 54. If I'm solving that for y, I would divide both sides by 2. Then I have y squared equals x minus 4 all over 2. Then I need to square root both sides. All right, heads up, kids. When we square root, that means plus or minus that square root of x minus 4 over 2. And how we type that into a calculator, we can't do a plus or minus key that doesn't exist, so we're going to type y1 as the positive square root, and y2 is going to be the negative square root. And when we see both of those graphs together, that will be the total function that we're trying to graph. And really, it shouldn't say solve the function. This is definitely going to fail the vertical line test, so technically it shouldn't be a function. So let's go to our calculator, and in y equals, we'll clear out what we had. For y1, that's the positive square root of, and then I've got x minus 4 divided by 2, and then we'll tap out of the square root and hit enter. For y2, here we've got negative square root, and then inside again, x minus 4. I want to be sure that's in parentheses. All of that is being divided by 2. And then when I go to graph, I'm going to hit zoom and 6 to get my standard viewing window back. Oh, and look at that. The first and second functions combined. What's that graph look like? It is a right parabola. So like what we saw in chapter 2, it is a parabola that is facing off to the right. Okay, before we move on, let's slide the calculator over here. We've got to solve this second function for y. I'm going to add y squared to both sides. That gives me y squared plus x squared equals 100. I'll subtract away the x squared from both sides. Y squared equals 100 minus x squared. And then to finish solving, again, we're going to have to square root both sides. Guys, the whole chapter is on radicals. We're going to have to incorporate radicals at some point, right? So y equals plus or minus square root of 100 minus x squared. That means in my calculator for y1, I'll type in that as a positive square root. And for y2, I'll type that in as a negative square root. And the two separate graphs will combine to draw that. It shouldn't be a function. It should say curve. They'll graph that curve as one unit. So back to the calculator. Let's go to y equals. We'll clear out what we have. Under y1, we want the positive square root of 100 minus x squared. Okay. Enter that. For y2, we want the negative square root of 100 minus x squared. And we'll graph that. Let's see what we get. Oh, cool. So it looks like we've got an oval shape, but really what this is the graph of a circle. If we are ever suspicious about what this shape is actually making, there is a zoom option called zoom square. It's option 5. If I choose that, it takes away the rectangular nature of the screen, and it will graph that in a perfect 1-to-1 ratio. So you can see, oh, there, it definitely is the graph of a circle, and there it's just having some trouble plotting those points. It does connect up there. All right, so describe the graph. It looks like a circle centered at the radius, centered at the origin with a radius of 10. And describe what graph that makes. All right. And that does it. Here's our 5.3 assignment. You can tell, yes, it is a long assignment, but remember, there are a lot of transformation problems there where it's really quickly just saying it's going up 2, left 5, vertical flip, stuff like that. So like the 19 through 25 odd, no graphing, just tell me what the transformation is. Very few graphing problems involved. So it looks long, but really it is really about the same length of assignment as the other ones that we've done. That is the end of section 5.3.